Now let us see what is meant by intermediate code generation. Once the source code is syntactically and semantically correct, even lexically correct, see lexical analyzer, syntax analyzer, and semantic analyzer. Under all these three phases, if it is syntactically and semantically correct, an intermediate code will have to be produced. Actually, this is also an intermediate representation. Many compilers consider syntax tree as an intermediate code, and it is taken as such for code optimization and code generation stages. Now, intermediate code is, as the name suggests, is an intermediate representation just before actual code is getting generated. There are several forms of intermediate code. Before, let us just understand why this intermediate form is necessary. What is the use of adding complexity to compiler by adding an intermediate form? Why can't directly after syntax analysis and semantic analysis, why the compiler can go ahead with generating the code? This question should be in our mind. Science people will be always asking questions. Why intermediate code? See, intermediate code is required because it helps the process of generation easier. When we in module 3 and 4, when we discuss about how a code can be optimized and how the machine code can be generated, we will know that. See, don't think that the compiler is going to generate the source code for whatever statements we have written. It's not a blind translation. It was before the initial stage of compilation. Now, the actual source code is not translated or compiled as such. Compiler it will take a lot of modifications to the source code. One simple modification will tell you all the comments which we have added will be removed. All pre-processed statements that we have included, like hash include, will have to be processed. All hash defined statements we have mentioned will be substituted with the actual values. All the variables, all identifiers like variables, function names, parameter value names, everything will be replaced with corresponding token values after adding them to symbol table. So the source code will undergo dramatic changes after compilation. On top of that, compiler will have to do some kinds of optimizations also on the code before the actual code is getting done. All these things can be easily done with the help of intermediate code. And that is the logic behind the generation of intermediate code. Once intermediate code is independently designed and if it is used, this intermediate code can be given as an input to the code generation and optimization phases, where all the processing things can be done with much ease. Syntax tree is an example for such a form. Now, I told you that there are different forms of intermediate code. If you can also develop intermediate code and sell to computer designer. I'm not joking. You will know that when you learn in many modules of compilers, you will see that majority of the problems in compiler designs are NP complete problems. Heuristic approaches are always open for modifications. Every compiler student, every student is free to suggest his own methodologies and algorithms to make the compilation better. Suppose that a new intermediate form is to be developed. It should be easy to produce and it should be easy to translate. Here again, see again translation. Our machine, our initial statement is getting translated to an intermediate code here. This intermediate code is again, it is getting translated to actual machine code. And in this example, we have used a format called as three address statement. See, this statement is converted to a three address statement. Details of this we will discuss in the coming days. Let us wait for that good day. Now to code optimization. See the order. After intermediate code is generated, we would like to optimize that. What do you mean by optimization? How an optimized code can be done? See, optimization has several features, several criteria. See here, producing faster and shorter code. Code should be faster. It should have fewer number of statements. Then it should occupy fewer number of bytes. And there are several other criterions also, like a code which is energy efficient, a code which can run with less power. So all these considerations can be given while generating the optimized code. See here we have a 60. Now to promote 60, here compare note that ID3 is of float and 60 is of int. So there is a semantic problem here. Int is getting multiplied with float. So it should be, instead of mixed mode, it has to be a real mode multiplication. 60 is forcefully converted. Here, in the semantic analyzer has truthfully gone for a function called int float. Now the code optimizer, when it looks through this statement, it sees that instead of 60, this forceful conversion y60 can be replaced with a 60.0. It alleviates the need for a function call. So such simple things which we may feel, it will add a lot of miracles to the target code being produced. Our code will be drastically modified. And all these things will be done in machine independent code optimization phase. So our code optimization phase, it is split into two modules. One module will happen just ahead of code generation. And that is meant by machine independent code optimization. And that happens here. See, this is just a quick example to digest what is being happening. Now the next phase is code generation. In code generation, it is the most expected thing. We have to produce the target code, not we. Here we is compiler. Compiler has to produce the actual target code for the target machine. Now there are several criteria. See, generating the correct code for correct target code for a given machine is a difficult task. Computer scientists have termed it a difficult problem. Code should be efficient. Before efficiency, correct should become correct, and efficient code should be generated. And when we do that, we have a lot of issues. One crucial issue is assignments of registers. These things we have primarily mentioned this in the art of program methodology sessions. Do you remember about a register keyword in C? There is a register qualifier called register, a qualifier called register in C. You can say register int I. What's meant by that? When we say int I, we are reserving a memory location of data type int. And when we add a qualifier like register, we specify the compiler that I should be kept in a register. What is this register? Registers are GPRs, general purpose registers like accumulator and BC, like that. Now when you keep something in a register, we know that it will be faster to access that. The fastest memory location is a register. So if you keep, but we know that we don't have much luxury in registers. Registers are very few, and if a programmer indicates that every variable should be in a register, compiler cannot accommodate that. Compiler can only, it should take a judicious decision now which of these variables should be kept in a register and which of these variables are to be considered as primary memory locations. And these decisions will have to be taken in the code generation phase.